In this video, we're going to be talking about two different types of mechanical waves, transverse and longitudinal waves. Now, a mechanical wave needs a medium to be able to transfer energy. Now, waves do not transfer matter, they transfer energy. A medium is a substance through which a wave can travel. Now, we also looked at electromagnetic waves, and electromagnetic waves do not require a medium to travel, meaning they can travel through a vacuum, which is not a medium. So we have two different types of mechanical waves, transverse waves and longitudinal waves. They have some pretty hefty differences between them. And here are just some examples and how they look like. First, let's move to transverse waves. So this is how a transverse wave moves. The wavelength is the same on each side. You can easily see the crest and the trough. This entire part over here represents one wave, and you can even calculate the amplitude, which is the difference between this origin point and the distance between the origin point and the crest, or the difference between the origin point and the trough. They're perpendicular to this origin over here. This origin is called propagation. Propagation means to spread, and this propagation over here, because it's perpendicular, it's able to move much more faster, and is also able to move much more easier compared to the longitudinal waves. Next, the thing about longitudinal waves is that they're much more complicated. Longitudinal waves can compress, they can have rarefaction. Compression is basically where the wave collides together. The particles in the wave collide together. Rarefaction is where the particles in the wave spread apart. Because of these differences over here, this part over here would represent one wave, we can see. And we can also see how longitudinal waves compare to transverse waves, because while a transverse wave would be going like this, the longitudinal waves, if I were to try to draw this, it would go something like this. So you can see some of the differences over here between the wavelength, and you can also see that this entire part would be one cycle, but this one cycle wouldn't exactly be equivalent to this one cycle over here. So longitudinal is where the particles in the wave spread apart or oscillate in a direction that's parallel, not perpendicular like transverse, but parallel to the line of propagation, which is this origin point over here, this line that's going through the middle. So now we're going to be looking at mechanical waves through a slinky. So for a transverse wave, since it's perpendicular towards this propagation, what would happen is, I'm going to have an example. It would look something like this. I'm going to try to shake it. You can see that, let's say that this is the original line over here. If we were to shake it, you can see how it's perpendicular. It's moving perpendicular to this line. So it's moving perpendicular. We can also see that over here. It's coming up to the crest, but then going back to the trough. This creates a perpendicular pattern. So this creates a perpendicular pattern. It's going up, but then coming down, and going up, but coming down. This is kind of like the perpendicular over here. This is how a perpendicular looks. Like we have the propagation over here, and we have the wave. It's just going up and coming down, going up and coming down. This is a perpendicular motion. Now, if I were to do it on a longitudinal wave, then we would see some compressions and some like rarefaction here and there. Yeah, I'm gonna do it like this. This area is compressed, this area is less compressed, this area has rarefaction, and this area is more compressed. This kind of acts like a longitudinal wave. The longitudinal wave goes parallel towards this propagation line. We'll show it in this example. So wait, I'm just gonna demonstrate transverse waves one more time. Keep your hands still, okay? But I'm gonna demonstrate transverse waves one more time. It's moving up and down, but the line is straight, but we saw it was moving up and down. This is going perpendicular because it's going up, it's going down, it's going up. We can see from there that since it's going up, it shows that perpendicular motion. But if I were to do longitudinal wave, it won't go sideways. It will match up exactly with the line of propagation. And because it's matching with that line of propagation, it won't go like side to side, really. And the thing is, it's going to stay on that, making it have a parallel motion. So like this. You can see how some areas are more compressed, while other areas are not completely compressed. You can also see how this is staying in the line of propagation, but for transverse waves it was not, it was going side to side. So longitudinal waves work like that. Some examples of longitudinal waves would be sound waves, but some examples of transverse waves would be light waves. So in this video, we talked about mechanical waves, which are transverse waves and longitudinal waves. Transverse waves move in a perpendicular motion, while longitudinal waves move in a parallel motion. Longitudinal waves have compression and refraction, meanwhile transverse waves do not. Both waves have wavelength, crests, amplitudes, and we can see how longitudinal waves, one wave could have has compression and refraction, but for the other one with transverse waves, it would go from crest to trough for transverse, but for longitudinal, it also goes from crest to trough, but it could also have compression and refraction in it. So if we were to transcribe this longitudinal wave, then it would look something like this. You can see that this area over here is much more compressed, but this area over here is much more rarefaction. We can also see this over here. This area is much more compressed, but this area is more rarefaction. So that's how we could potentially transcribe this in like transverse wave form.